Welcome to our next installment of the Energy Storage at PNNL webinar series, where we're exploring some of the latest topics in energy storage. Today, we are really focused on developing a flow battery. And flow batteries are one of those emerging technologies that we're seeing to be able to address the duration that we need for high renewables penetration, the storage durations that we need. And we're honored to have Wang here. I'll give to present on the flow battery. Give you a little bit of context of what we're trying to do in this series on the next slide. This is in support of the new DOE grid storage launchpad that's being launched at PNNL. And the real focus on the grid storage launchpad is to take these new technologies like redox flow batteries, and how do we get those developed and deployed faster than we have seen historically in other technologies. So, it's looking at the materials level. How do we do that under rigorous grid duty cycles? So we know how these are going to perform, and how do we make those life estimates of or predictions on these technologies as we move forward. So in that, we're exploring different technologies, different aspects that come in and will, basically help guide the outcomes of the grid storage launchpad. On there. And there you see the link if you need more information. So without further ado, I'd like to get into our today's seminar. We're happy to be joined by Dr. Wang, who is an internationally recognized expert in the field of large-scale energy storage technology. He is currently director of the Energy Storage Materials Initiative at PNNL, which is a multi-million-dollar effort to look at developing the artificial intelligence, machine learning underpinnings needed to accelerate our predictions of technologies and develop that. Wei also serves as the chief scientist and technical lead on the stationary energy storage R&D, which covers a diverse portfolio, including redox flow, lithium ion, and sodium ion batteries. Dr. Wang joined PNNL in 2009 after receiving his PhD in materials science and engineering at Carnegie Mellon University. So with that, Wei, we're looking forward to your talk. We'll try to go, and then if you have questions throughout the presentation, please put those in the chat, and we will have time at the end to answer and address those questions. So Wei, thank you for joining us today, and please take it away.
Thank you, Vince. I'm gonna share my screen. Can you see it?
We can, thank you, Wei.
Okay, great. Hello, everyone. Good morning and good afternoon to some of you in the East Coast. My name is Wang, and we'll be giving a overall introduction on how to develop a redox flow battery. So from previous seminars, I assume most of our attendees has either a science or engineering background and has been in the energy storage for a little bit, but want to learn the difference between the flow battery and with other battery systems, the differences. So I will focus my talk on that aspect and also some of the current research needs in the redox flow batteries. But if there's a jogging that you're not aware of it, or some questions, please feel free to ask or send me email afterwards. So to start with the talk, we know that we have US government has a decarbonization goal of 100% carbon free electricity by 2035, and by 2050 we need to reach the net zero emission of the whole economy. So to reach this goal, it's very feasible to envision that a lot of renewable energies that have no carbon or reduce the carbon footprint will be joining the electric grid to provide the power. There's a study estimate that to reach the those goals by 2030, there's 1 terawatts of the electricity from the renewable energies to reach. So from that calculation, there's an estimate that if we're going to switch 80% of our annual electricity to renewable energy source, we need to develop 12 hours of energy storage for 100% that even longer hours will be needed. And that's precisely the reason that DOE has issued this energy Earth shot on the non-duration storage shot to reduce the storage cost by 80%, storage hours over 10 hours in 10 years. And redox flow battery is a very attractive technology for this application, and we will be talking about that from the fundamental working mechanism, why we say that flow battery is a promising choice. So this is a working mechanism comparison between lithium-ion battery and a redox flow battery. The lithium-ion paper is from the website of the DOE EIE office. So as you can see, for the sorry, did I just do some switch? Oh, sorry. So yeah, as you can see, the charge and the discharge of the lithium-ion batteries. This is what widely known a rocking chair mechanism that the lithium ions will traveling between the cathode and the anode during the charge and the discharge process. And this is a redox flow battery. The difference is very obvious. First, the primary energy in the lithium battery is stored in the solid electrode. So most of the reactions is either lithiation or delithiation reaction, or the alloy or de-alloy reaction, depending on what kind of materials you have there. But in the redox flow battery, the energy is stored in the electrolyte, and the energy conversion reaction is mostly the reduction reaction happened in the solvent. For this talk, we will focus on the aqueous solvent, so that will be happening in the water. And based on this different mechanism and then the different architecture, there's many different characteristics of the flow batteries that is suitable for the non-duration energy storage. The first one is the redox flow battery. The architecture is probably the NA battery architecture that can decouple the energy and the power, so we can singularly increase the energy over the power. This will also decouple the cost association between the energy and the power when you design a long duration battery. So you don't need to pay the cost of the power component that is unnecessary for the long energy duration. And we also consider the recycling. If we consider the after the service life, there's a recycling cost for the lithium-ion battery or another solid-state battery. But redox flow battery, from the working mechanism, the material itself is not going through any degradation or structure change. It's merely going through the valence change of the redox reactions. So you theoretically you should be able to recover all those materials. But another consideration is the safety. So the redox flow battery is generally considered a very safe redox battery chemistry. Mainly because several reasons. One, because the cathode anodite reactive materials are physically separated in different tanks, so the chance of them to mix together and cause a thermal runaway is very small. And for aqueous batteries, of course, a major constituent is water, which has a high thermal capacity, and also. Not all the flow battery, but at least for the vanadium redox flow battery, has a very unique charge discharge thermal characteristics. So when you charge, the reaction itself actually is endothermic. So the temperature during charge increase is not that significant as compared to the lithium-ion batteries. So this is very appealing if you use a battery in a hot environment. And so for that. This data is a bit dated. This is before the pandemic. There's quite a bit of lithium-ion battery fire in South Korea, and I think recently there's battery incident in Arizona early this month. But for large scale, long duration energy storage, safety is a very important consideration, and the redox flow battery has a very appealing attribute in the high safety of itself and its materials. So I'm gonna show a little bit about the history of the redox flow batteries. So nowadays, nobody will talk about in the same sentence of the redox flow battery and aviation, but in fact, the origin of redox flow battery is actually first generated to power airship. Yeah, it was actually the zinc chloride flow battery was designed and created to power the first controlled aviation that was done by this airship in France in about 1984. And the chemistry and battery was designed by a Frenchman called by the name of Charles Reynard. He designed this zinc chloride battery in the back of this propeller. So by control how close the zinc, the distance between the zinc and the hydrochloric electrolyte, it controls how much power it delivers. And his colleague by the name of Arthur Krebs designed all the electric motor, and he later actually designed quite a bit of modern automobile, like steering wheel and electrical brake, those type of things. But after from this figure, you can see after that there's a very little development over a very long period of time, and it's only around 2009, 2010 that this technology started to pick up a lot of interest, and over the last 10, 12 years, there's quite a bit of different redox flow batteries, include different chemistry, different architecture, different materials has been reported. And for a little bit of fun fact for you, this is the specification for that battery that's powered the La France. So if you have interest, you can calculate the energy density needed for that battery. I'll leave that to you. And so the different type of the batteries, and they beyond the traditional both solid, both liquid redox flow battery chemistry, there are quite a bit of new architectures came up. Some of them, for example, this is called semi-solid, which basically has nanoparticles or colloid of materials, solid materials functioning as the energy barrier to suspend it in the electrolyte and pump this through the electrode and the electrolyte tank. And there's a hybrid flow battery in both hybrid with solid and hybrid with the gas electrode. For example, the lithium hybrided and also oxygen hybrided redox flow batteries. And they recently furthermore hybrid with the photoelectrode to use the photo to charge one side of the electrolyte and the discharge through the redox reactions. So, and I want to show you about this material diagram. So before 2010, most of the research is concentrated on the inorganic materials, zinc, bromide, those are the early systems, and sulfur. And in recent years, there's a great effort on using the organic materials as the redox active materials for the redox flow batteries, and I will be talking about that a little bit. The early redox flow battery chemistry, iron chromium redox flow battery that was invented by Larry Suller from NASA, was the first, probably the modern sort of modern time redox flow battery that use both sides has the liquid electrolyte. One side use iron, the redox reaction between iron 2 and 3, and another side between chromium 2 and 3. The problem with this system is a significant crossover. So the system, they end up have to use a mixed electrolyte solution. So actually both sides has both redox element. And the chromium side has no electrochemical activity, so they often require this side to be operated at a elevated temperature. Also, sometimes the electrocatalyst was added in the system. And later on, all vanadium redox flow battery was invented by Professor Maria Skolarsky from Australia, and this is probably currently the most widely studied and developed redox flow batteries with the largest systems. This figure shows before the pandemic of the 200 megawatt, 800 megawatt vanadium all vanadium system that was built 2 or 3 years ago in China, in Dalian province. This system, one very prominent characteristic is that it uses single element for both sides, just capitalize on the different valence between vanadium 2 and 3 and vanadium 4 and 5. In this way, they effectively suppress the crossover. So once the material crossover to the other side, it will still be the same element. So the cross-contamination is greatly reduced. That still have some issue. I will be talking about that too, but compared to iron chromium, this is a much more successful chemistry, and it has the issues of the no electrolyte concentration, no stability, those type of issues that we will be discussing. We'll talk about a little bit for those of you that haven't worked on the redox flow battery about the major component and the structure. So one redox flow battery normally consists of 3 major parts. One is the membrane, like the one showing in between, in the middle of here, and they normally use graphite filled electrode that was compressed by the current collectors and the end plates. And several of the cells compressed together that become a stack. And this end plate normally also hosted the manifold that functioning as to give the system a proper flow distribution. And that is quite important in designing the largest cells. And those different cells are collected in some kind of this way in a bipolar structure. It's very similar to the fuel cells, so it's very easy to scale up the redox flow battery. You just need to put more cells back to each other, and several of those unit cells will form an arrow of stack that further form a system, flow battery system that become to provide the energy storage. In terms of the design parameter, Professor Frank Wash at the University of Southampton actually have a very good paper called the engineering aspect of redox flow battery. So they published on this paper. Yeah, for more details, please refer to that paper. It gave a lot of good information. 2 major design parameters for stack is pressure drop and shunt current. You need a certain pressure to move the electrolyte from the first cell to the last cell to circulate the electrolyte, but we have many reasons to reduce that pressure drop, to reduce the pump power consumption, and also to reduce the friction between the electrolyte and the piping. And flow battery also have a shunt current issue, which basically from this bipolar design, so from the first cell to the last cell, actually there's a pressure drop, not pressure drop, sorry, a voltage drop. So there's a internal current will be generated due to that voltage difference, and we certainly want to minimize that. So there's different ways to minimize the shunt current by increase the flow length, or basically increases the resistance between the first and the last cell. In terms of the flow battery operation, again, on this Professor Wash's paper, there's a lot of good discussion on what kind of different factors that affect the performance of a redox flow battery. I will just talk a little bit about the crossover, since this is a phenomenon that is different from the lithium-ion battery. In lithium battery, ion battery, you normally don't have active materials cross from one side to another. But a crossover in the redox flow battery is a very common phenomenon because we don't have a perfect membrane that can separate the two sides of the electrolyte. Because of that, the active ions or molecules often cross from one side to another, depends on the different driving force. And once they cross over, in some conditions, they will react with the native ion. So that will cause a self-discharge reaction, will further cause the two sides of the balance to shift away from each other. I'll show some of the different consequences of this crossover to highlight that this is actually a phenomenon that needs to be managed, need to be controlled in the redox flow battery. So the upper one is showing a lithium-based flow battery, redox flow battery. The SOC change during the cycling, you can see the positive, the SOC shrink while they not shrink, it's shrink while also going down. And the negative side is going up. But if you have a separator-based flow battery, they actually goes to opposite direction. The positive side will go up while the negative side go down. So those crossover has to be examined by the different driving the iron crossover mechanisms. For example, in the lithium, the diffusion is a major driving force, while in the separator-based flow batteries, the convection is a major driving force. So those has to be all considered. So now I'm going to switch to talk about the current research errors. Flow battery is pretty easy to design as long as you have two redox couples you can dissolve in the water and have sufficient of the voltage difference. Then you can form a redox flow battery. But in terms of the research, it's actually quite complicated. The research error across a very wide spatial and temporal space. For example, we have electron sharing, electron jumping, excitation at a picosecond or picometer level. That is very difficult to both modeling and observation. And then on the one step higher on the nanoscale, nanoscale that, sorry, we have the ion transfer that basically exists in membrane and also in the electrolyte. And going upper, we have flows that going over the electrode surface to finish the redox reactions. So to really go deep into the flow battery research, you have to understand all those phenomena to employ different modeling technique, characterization technique, and the material synthesize and the design to come up with better redox flow battery materials for the redox flow battery application. Some of the general research error include in the electrolyte, membrane, electrode. There's also research on the stack and the reliability, and currently there's also a small error of non-aqueous redox flow battery that mostly for special use. I will not get into the non-aqueous flow battery error. So what is the major challenges we need to deal with on the redox flow battery? So one issue is the no energy density. You're probably already aware of this. This is a figure that's showing the energy density of most of the redox flow batteries. Most of them you can see for the two redox flow batteries that have both liquid on anodite and cathodite. Most of them are actually lower than 50 watt-hour per liter, definitely lower than 100 watt-hour per liter. And the lower end lithium-ion battery is this outer line of 200 watt-hour per liter that are based on the lithium iron phosphate with graphite anode. So one major issue in the redox flow battery is to increase the energy density by increase the concentration of the electrolyte and also increase the temperature window. And those two are often related. The temperature stability often related with its concentration of the particular temperature range. And also we have a choice of limited raw materials, both in the inorganic system and in the organic systems. If you look at the periodical table, if you want to find inorganic materials that has good redox capability within the water electrolytic window, it's actually very limited. And the same thing also exists in the organic-based redox flow battery that I will be talking about. So the technology and research needs and development, I will be talking about how we can tuning the Solvation chemistry to increase the concentration of the inorganic based electrolyte, and talking about some of the development used in the organic based electrolyte. So I will be talking about some of the commonly used strategies that to increase the concentration of the electrolyte, and they also increase their stability. So the first one is design the contact ion pair. So this is a commonly used method in the Solvation study. So for the vanadium redox flow battery, it has an issue of the vanadium 5. The vanadium 5 electrolyte was precipitated at a higher temperature. The figure showing here is this the stack image after cycling many cycles at room temperature. We took it out, we took it apart, and then after this is cycling at a temperature higher than 40 degrees C, you can see the brown reddish particles that deposited on the graphite field. Those are the V2O5 solid. So we did some of the study that showing the vanadium 5 hydroxide will actually at a high temperature, when it gains some energy, will go through a deprotonation process, become hydroxide, and this species will further polymerize and then nucleate and become a V2O5 precipitation. And once we understand that, we found that this deprotonation is generated by the electron sharing between the oxygen and the vanadium. So we introduce another co-solvent, the hydrochloric acid. So the chloric will form a contact ion pair with the vanadium to share the electron with vanadium. By this way, we can stabilize the electrolyte quite a bit, increases the energy density by, I think it go up to 2 molar, 2.5 molar. And then the temperature window also increased quite a bit. This is a technology that have been licensed to several companies. Another example of the design of the contact ion pair is the zinc polyiodide. So I came from a lithium-ion battery PhD study. So my goal was always to increase the energy density. Same as in the redox flow battery research. So what we found is this iodide chemistry. So iodine does not dissolve in water, barely dissolves in water. It's a solid, but when it has the excess, when it is present with the iodide, it will actually form a triiodide. So the triiodide has a huge solubility. I think it's around 7 molar in the water, so that translates into a very high energy density. So based on that, we developed a zinc iodide flow battery. This flow battery has some of the very interesting characteristics. It has a sort of what I call it an ambipolar electrolyte. Basically, both the anion and the cation are active energy bearing species. So normally for example, in the vanadium flow battery, the anion, the sulfate ion is not active. It's just a compensating ion. But in this design, both ions are active, and it has a bifunction electrolyte. The zinc ion function as both the charge carrier and the energy bearer energy bearing ions. So this chemistry was able to reach a very high energy density. We were able to demonstrate the 3.5 molar. I think we have a bit of charge and the discharge at 5 molar, but at that point the electrolyte become very viscous, very viscous. It's difficult to do the charge and the discharge. So after the 5 molar, the energy density actually somewhere can compare with the lithium iron phosphate based lower end lithium ion batteries. I think there's other group did the first study on this chemistry currently still remain one of the highest energy density redox flow battery chemistry. But this system has a problem with the opposite to the vanadium system. It precipitates out at lower temperature. And the exact reason is because the triiodide is pretty happy in the water until it has a cation move closer to it. In this case is the zinc. When the zinc close to the triiodide, it will actually strip one iodide away and left the iodine to precipitate out. And this is, I believe, exothermal reaction. So it happens more on the lower temperature. And once we understand this, we can design another contact ion pair to prevent this electron sharing. So the one we choose is a simple alcohol that we know that will complex with zinc. And after we add the ethanol 5 or 10% in the electrolyte, you can see the NMR signal change. But this addition of the simple alcohols actually can stabilize the zinc iodide electrolyte at a quite low temperature at a high concentration. This is the cycling performance. So the contact ion pair design is actually a very effective way to design the higher concentration electrolyte if the active materials precipitate out due to some kind of electron sharing. Then you can tune the solvation chemistry to bypass that, to overcome that electron sharing. So another one I want to introduce to you is sort of a adding active. So if the two active ions are easy to dimerize, to polymerize, then there's a way that you can add an additive to separate them out to present their polymerization, and that could stabilize the electrolyte as well. And this was also done on the vanadium electrolyte. So this is what we understand the whole process of the V2O, the vanadium 5 precipitation process. I talk about this deprotonation process and how to prevent them. And furthermore, if we can present the clustering after the dimerization and polymerization, then we can also stabilize it. And that actually can be done by this bi-additives, the magnesium and the phosphate salt. This mechanism is very complicated, but in general, some of the anions and cations forms hydrogen bond or non-covalent bond with the vanadium 5 species that in that way effectively separate the electrolyte further apart, prevent them from precipitate. So this is the in situ NMR, which shows that for those peaks are the indication of the precipitation of the vanadium 5 solid. It's either a V2O5 or V2O3 solid. You can see in 2 molar without the additive, you can see those peaks much earlier and they around 250, 270 minutes. But after you add the electrolyte, those peaks show up much later, around close to 18 or 19,000 minutes, much later than the one without the additive. So this is also an effective way that you can stabilize the electrolyte. This is about I'll skip this. Basically, this tells that that those shows those higher order vanadium oxide. When you add the additive, there's a lot less of those species. Therefore, you can prevent them from further aggregate, become solid to precipitate out. And this is the performance of this electrolyte compared with different valence. I'm going to switch to talk about the organic system. As I showed before, since 2009, 2012, there's a rapid increase of research interest in the redox flow batteries using the organic materials. And the reason behind that is some of the stack development that actually was done here, that we were able to increase the power density of the flow battery, vanadium flow battery stack. You can see from originally around 80, 160 milliampere per centimeter to all the way to 400 milliampere per centimeter square. This is all kept on the efficiency over 75%. What that does is it significantly changes the cost distribution of the overall vanadium systems. You see from here, early on, the membrane is a major cost for one of the major costs, 42%. But once you increase the current density, now the chemical itself will become the major cost driver at 60%. So we have to find some other cheap materials to replace the vanadium as the energy bearing materials. And as I said before, if you look at the inorganic transition metal ions or other elements of their redox potential and form and consider their availability in the Earth's crust, there's not a whole lot of choice. So that's the reason actually why the whole field is kind of jumping into the organic system. The idea there is that we could get away from the resource restraint, and also in the organic material development, there's more space for us to explore, to design different materials. That didn't turn out quite true. I'll talk about that also. So in the organic system, one issue we're running into right away is we do have a lot more choice, but what is the right choice? This is a question that a researcher needs to answer. Normally it's very seldom that you will encounter a core structure that has the right electrochemical and also solvation properties that can be used in a flow battery right away. Somehow you have to do some derivation of some kind of functionalization to change the property a little bit. Like the figure showing here is how this type of functionalization changes the electrochemical characteristics, change its redox potential, and also change its solvent, its solvation, the solubility. So this is a Philizone structure, the number one, a pristine structure. This one, we know it has a good electrochemical property, but it barely dissolves in the water. So we have to make it somehow have a good solubility. So there's quite a bit of different functionalizations out has been proposed, and we did a DFT calculation to figure out what those functionalization will do to its redox potential and also the solvation energy. So by this way, we can identify the couple of the good ones. Two of the good ones. One is with the sulfuric acid, functionalization, and this is the one we choose to achieve both ideal redox potential and high solubility. This is most of the currently, if you are working on the redox flow battery on the organic materials, most of the study are going through this type of route. So in the organic space, most of the time we capitalize on the preferential solvation to increase the solubility of the organic materials. What that means is for the organic materials that it's in this case the Philizone, the electron distribution is on the pristine material molecule is symmetric. So this is why it does not dissolve in the water that much. And to achieve the solubility, you have to create some kind of symmetry in the structure that those asymmetric distribution of the electron density will intensify the solvation with the water, with the surrounding microenvironment in the electrolyte. So this was done. This was showing the DHPS has a much more asymmetric electron distribution, and this asymmetric electron distribution is confirmed on the NMR study. You can see the peak shift from the sulfuric side of the protons is much more bigger than the other side. So through this, we can achieve a pretty high concentration of the DHPS. I believe it's around 2 molar. So this is the cycling study. This material is not very stable compared to some of the later materials we discovered. And we also did a study on the degradation mechanism. This is actually a very important topic that has not, in my opinion, collected enough attention on in the research field on how we can make the molecule more stable in the long cycling, because flow battery are deemed, if we want to support the electric grid, we need to have a stable cycling for many, many years. So this is one of the degradation study that's showing different substitution pattern and how that will affect the stability of these different molecules. So yeah, we have been doing the organic flow battery development for the last 5, 6, however long that is. And our basic assumption, as I mentioned before, is there's a lot of more choice in the organic space, right? But it turns out the organic in the organic space, there's also a very limited library. These are the organic structures that has been reported for the flow battery application with limited success. And another issue with the organic based flow battery is what we just mentioned, that we haven't been able to demonstrate a significant period of time of the stable cycling. Most of the organic flow battery cycling looks like this, right? Quickly degrade, and most of them doesn't even they don't even show this none of the cycle. Most of them, and they say show 1 week of the cycle. So we haven't been able to showing a long-term cycling that sufficient enough to be considered for utility battery. So for that, I will talk a little bit about some of our study, that effort that try to enlarge the chemical space of the organic systems and also improve its stability. So the fluorino, this material, we know that it's very stable. This is a previous study of this material reflects at elevated temperature for more than half a year, and the before and after data spectra showing that the structure is not degrading. But this material have a issue is not a reversible. You cannot put it in the battery. There are attempts to put it in the non-aqueous system. They can cycle, but the capacity quickly fade. And in the aqueous system is even worse. Within 5, 6 cycles, the capacity almost dropped to 0. The issue here is the reversibility. So actually, after the ketone is the fluorino is a ketone structure. The ketone is known for 2 electron reducing capability, very phosphor reaction. But the dianion will oxidize at the elective potential. Then the forms alcohol. The alcohol, if you want to bring it back, the potential will be much higher. Over 1 volt versus the silver chloride. So you cannot basically you cannot use it as an anodite anymore. That's basically the reason why the capacity in the aqueous system drops so much. showing here is the CV study. The orange curve, the orange trace is in the acetone, the acetone nitride without water. And as you gradually add water, you can see those peaks gradually disappear. By the time of the green line, this oxidation peak already disappeared. So the question here is we need to make this material reversibility. And this is very important because there's a lot of organic molecules that has this type of irreversibility, or called partial reversibility. They have some kind of, they can go some kind of a redox reaction, but not fully. So what we found is we identified that this is basically caused by the protonation. So we came up with a strategy that to decrease its tendency to protonate, to increase basically by lower the pK to make the material easier to deprotonate, to generate those ionic species. So we did a whole lot of series study on putting on different of the electron withdrawing group that will make the proton easier to go away. And we identify, they shows by adding electron withdrawing group, you can change lower the pK of both the OH and CH. So both proton can be deprotonated, that contributed to a 2-electron reaction. And we also did a little bit of
Way to interrupt, sorry. We're approaching 10 minutes till the top of the hour, and we've got quite a few questions, so just wanted to bring that to your attention.
Okay, I will jump. I will go fast. So this is a study on, again, increased solubility, and this is a full cell study that shows a stable reactions. I'll skip the capsulite. I just talk a little bit about electrode research. There's a whole lot of research on the electrode. The electrode is basically considered to taking electron. Most of the time they're using graphite field, but you can deposit some kind of metal or metal oxide to increase its charge transfer process. And a little bit of membrane study. Actually, I consider membrane is one of the most under investment area. A lot of phenomenon in the flow battery is related with membrane, that primary functioning as a separator that need to provide high ionic conductivity also, and selectivity. So it's many times two opposite properties. So some of the research was geared towards to minimize the pore size and select as a increase its selectivity, like some of the work we did to ladder the pore size to increase selectivity, while also increase the backbone's hydrophilicity to increase the conductivity. I probably need to skip this. This is basically talking about the diagnosis. Most of them currently is done by monitor the voltage. And this is one we developed using the ultrasonic method to determine the SOC, and also can determine the side reactions. Some of the modeling work, I think I will skip this. So in the summary, I think a redox flow battery development is a multidisciplinary research field that need a lot of different expertise and a community effort to move this field forward. And currently we're focused on identifying active materials that can provide high concentration, high energy density, and low cost. Acknowledgement, most of this research I show here are funded by DOE Office of Electricity Energy Storage Program, and some of them are by one of the PNNL's LDRD project, and my colleagues who actually did the work. With that, I will conclude my talk.
Well, thank you, Wei. And so I'll get right into it with we got quite a few questions coming in for that. On here. So one of the first ones that came in is talking about the needs for longer duration. we're seeing a lot of the battery technologies out, or flow batteries are still at that 4 hour, but we understand that physically you can just increase that tank size. But what's the real challenge for us to get to that 8 to 12 to 48 hour type storage durations with the flow battery?
Yeah, so for the, we mentioned before that the flow battery is a unique architecture. You can simply add more tanks to increase the hours. But here is the major question, I think, is still we need a consideration of the volume and the footprint. If we are consider a large scale energy storage with 10 hours or for 2 weeks as 176 or some hours, then the current concentration, at the current concentration, the system will be very big, will be huge. The footprint will be prohibitive in municipal areas. Probably can only do it somewhere in a very rural area where the real estate is very cheap. So we have to, in my opinion, we still need to develop the flow battery electrolyte with much higher concentration.
Okay. Cost of those elements comes into play in terms of reducing it. I know a lot of our work has been moving from vanadium, which has price fluctuations, it's commodity material, to something we can control. We've seen other people move towards iron-based systems and more earth abundant. And that lower cost will help drive that also. Is that correct?
Yeah, that's definitely the goal. In fact, it is primarily the cost consideration that drives the field to the organic materials. Of course, there's also a sustainability issue. We don't want to always mining the earth to get the active materials. So for the vanadium system, there's some discussion on a business strategy called renting. So this is basically based on that you're not really consume the vanadium material. You are basically just use it for the redox reaction, and after the service life, you should be able to get all those vanadium back. So that's one on the business side of the effort to sort of elevate that cost of problem. But on the material side, we are developing the organic materials. Right now, those developers are still in the lab system. If we indeed identify some organic materials, molecules that can do the job, then we will be facing the question of how to scale it up, how to manufacturing those organic molecules in large scale that will be able to meet the need of the nation for the energy storage. So yeah, those are the very, very important questions.
All right, thank you. Another question we had just asked about comparing the round trip efficiency of flow batteries to other technologies. Where do these typically lie? And again, we're looking at that basic kind of component level or the battery level. Of course, when you put it into a system, you've got the power electronics and other round trip efficiencies, but it's most fundamental. How does that compare?
Right, so on the cell level, most of the vanadium flow batteries will be able to depend on how hard you drive it. If you any other current density about 80, 100%, normally you can reach efficiency above 85%. A well-designed system probably can reach 90% either as well. So one thing very important to notice is the way that the flow battery and the lithium-ion battery measure the rate capability is very different. In flow battery, it's normally the rate is measured at a milliamp hour per centimeter square, and in the lithium battery, most of the times the number used is a milliamp hour per gram. So if you if you do a conversion between those two numbers, you can actually drive the flow batteries much harder at a much higher rate.
Okay.
Yeah, and with the system, I mean, anything you add onto the system, you will bring that efficiency down from the cell level. I mean, if you add, consider the larger pump, the pump consumption is pump power consumption is a factor that the industry always trying to minimize, because that's basically a parasitic loss.
Okay. Trying to get a few more there, and we've got Ryan Franks on the line too. One of the questions came in talking about decommissioning costs. Is there any significant difference that you know of between flow batteries and other technologies that are out there? You touched a little bit on it on the renting or the leasing model for vanadium systems, but
I actually haven't had any experience on that.
well, maybe we'll touch base. Ryan, do you have anything to add on that, or?
Yeah, yeah, there is a couple industry participants certainly are investigating the reuse of and renting, leasing specifically of vanadium systems. And obviously end of life is becoming a big and very important consideration with all types of energy storage systems, including flow battery systems. But Wei, thanks for your presentation again. One of the things that I think related to some of those business models is there's a lot of news lately around lithium-ion supply chain problems. Is there anything like that that's occurring in the flow battery industry as well?
It happened before, actually. I remember about 5 or 6 years ago, because of the some of the mining accident and some of the factory shutdown, there was a huge spike of the vanadium price. So I believe the vanadium, if right now, because the market deployment is compared to lithium-ion battery is still small fraction. It's not that prominent on the supply issue, but if this technology is getting off and with more and more deployment, this issue will become more and more severe.
Okay. Hey, Wei, we've seen, with a lot of the work you presented, we're still aqueous based systems, and trying to go that route to ensure the safety of the system by having it water based. What needs to happen for non-aqueous flow battery technologies to make that next leap? Or what do you see as the potential for that?
I think a non-aqueous flow battery is a much more challenged research field compared with aqueous system. I mean, in terms of it's also a very rich scientific research area with lots of fundamental science that one can dig in and gain more understanding on the solvation, on electron, ion charge transfer, those type of fundamental understanding of the systems. But in terms of practical use, it will be very challenging compared to the aqueous system because of the couple of reasons. One is non-aqueous system tend to have a much higher viscosity. So that will normally make the system worse in a lot of different aspects, like you have a higher pump consumption and your conductivity is low, and you need more pump to move the liquid. And the second thing is once you move away from proton, your conductivity lower automatically for like 2 orders of magnitude probably. And that in the system that shows your rate capability will be much lower. So to reach a certain rated power, you need a much larger system. But I do think the non-aqueous system has some niche market. For example, if it's in a place that require extreme low temperature, then the aqueous system just purely just can't do it. You have to go to non-aqueous. So some of the special use case we have to develop the non-aqueous systems. For example, if we all move to Mars, we probably have to have a non-aqueous system.
All right, well, thank you. I noticed we're at the top of the hour, and so sorry, apologize if we haven't gotten to everyone's question today. Thank you all for your input and questions as we move through. I would encourage you, if you have other questions, reach out to us directly, and we can try to continue that conversation. If we can pull up that last slide, I want to present what's coming up next in our series here. So as you know, as we talk about the grid storage launchpad, you've seen things like today on the redox flow battery, where it is the materials development. It is developing it with the cost structure. But critical to that also, to us being able to accelerate these new technologies, is understanding where they're going to be used. in there. And so the next couple seminars that will be present are really looking at that use case and what's driving that. So May 12th, Jeremy Twitchell from PNNL will talk about the trends in state energy storage policies. What are going to be those future drivers for how these new technologies are used? Another one that kind of goes along with that, Rebecca O'Neill will talk about energy storage for social equity. So as we start looking at that local environment in communities and how storage can play a role, that's another use case that we need to consider as we're doing development of these new technologies. And then on June 9th, Srinivas will be talking about using buildings as storage assets. And so those are our next three. We hope you join us for those seminars, and we'll continue on and look forward to seeing you in a few weeks. Thank you very much. Thank you again, Wei, for your presentation. Bye.
Thank you.